Hey Vamsi. This line introduces the core problem. The SpectralClustering results are very sensitive to how many clusters, NCLUSTERS, we choose. Even a small change in this number can lead to very different clustering outcomes. This is what we need to improve. The overall goal of this problem is to find the best way to set up the SpectralClustering algorithm. It's all about getting reliable and consistent results, no matter the number of clusters we use. This section is all about exploring different ways to deal with the problem mentioned above. It's the problem-solving stage. We're looking at various techniques that can make our SpectralClustering results less affected by the choice of NCLUSTERS. This strategy focuses on the NNEIGHBORS parameter. Increasing this value considers more data points when building the relationships between them, making the clustering more stable and less sensitive to the NCLUSTERS parameter. Here we focus on the GAMMA parameter. A smaller GAMMA makes the relationships between data points smoother. This smoothing effect often helps to reduce the sensitivity of the clustering results to the chosen number of clusters. This option suggests trying a different way to define the relationships between data points. The affinity matrix, using a different matrix, such as nearest neighbors, can potentially create a more robust clustering result. Scaling the data can be beneficial for many machine learning tasks, including this one. It helps to ensure no single feature dominates the calculations. However, it does not directly solve the core problem of NCLUSTERS sensitivity. It's a general improvement, but not directly related to this specific issue. This is the desired outcome, a clustering method whose results are less dependent on the specific number of clusters chosen. The strategies proposed above aim to achieve this improved robustness. The quiz problem highlights that the spectral clustering algorithm's results are heavily influenced by the number of clusters, n_clusters, parameter. This means that slight changes to n_clusters lead to significantly different clustering outcomes. This sensitivity indicates a potential problem with how the data is represented before clustering. We need strategies to make the results less dependent on this parameter. The core of the quiz lies in identifying ways to make the spectral clustering results more stable and consistent even when n_clusters changes. This involves exploring ways to improve the robustness and reliability of the clustering. We are given several options, and we need to determine which ones would help address this sensitivity to the number of clusters. Increasing n_neighbors considers a broader neighborhood of data points when building the affinity matrix, which spectral clustering uses. This broader view lessens the impact of noisy data or local structures that might otherwise unduly influence cluster assignments, promoting more robust clustering results. A larger neighborhood creates a more global representation of data relationships, making it less sensitive to the specific choice of n_clusters. The parameter, gamma, in the radial basis function, RBF, kernel affects the width of the Gaussian function used to compute similarity between data points. Decreasing gamma widens this Gaussian, making the similarity between points less sensitive to small differences in their features. This results in a smoother affinity matrix, and consequently, a more stable clustering outcome less dependent on the precise value of n_clusters. The spectral clustering algorithm uses an affinity matrix to represent the similarity between data points. The default is often an RBF kernel. Using a different affinity matrix, such as the nearest_neighbors option, can lead to different representations of data relationships. This alternate representation might be less sensitive to variations in the n_clusters parameter, providing a more robust clustering solution. While scaling data using standard scaler is a crucial pre-processing step for many machine learning algorithms, and a good practice, it does not directly address the problem of sensitivity to n_clusters. Scaling helps ensure that features with different scales don't unduly influence the results, improving overall clustering quality. However, it doesn't inherently make the clustering results more robust to changes in the number of clusters. Okay, let's talk about clusters. The core problem is that the results of the SpectralClustering algorithm are super-sensitive to how many clusters, NCLUSTERS, you tell it to find. This means a slight change in the number of clusters requested can drastically alter the results. The goal is to make the results less dependent on this specific parameter. Okay, let's talk about clusters. The core problem is that the results of the SpectralClustering algorithm are super-sensitive to how many clusters, NCLUSTERS, you tell it to find. This means a slight change in the number of clusters requested can drastically alter the results. The goal is to make the results less dependent on this specific parameter. This refers to the specific machine learning algorithm we're using to group similar data points together. It's a powerful method, but as we've seen, it has a sensitivity issue with the number of clusters you specify. This refers to the specific machine learning algorithm we're using to group similar data points together. It's a powerful method, but as we've seen, it has a sensitivity issue with the number of clusters you specify. This is the information we are working with. The data points are what we're trying to group into clusters using the SpectralClustering algorithm. The quality of the clustering depends on how well the algorithm interprets the relationships within this data. This is the information we are working with. The data points are what we're trying to group into clusters using the SpectralClustering algorithm. The quality of the clustering depends on how well the algorithm interprets the relationships within this data. The core issue. The SpectralClustering method is too sensitive to changes in the number of clusters we specify. A small change in the input value drastically changes the results, making the process unreliable. Our aim is to improve this. The core issue. The SpectralClustering method is too sensitive to changes in the number of clusters we specify. A small change in the input value drastically changes the results, making the process unreliable. Our aim is to improve this. This is the question we're trying to answer. We need to identify approaches that make the SpectralClustering algorithm's results less sensitive to the number of clusters we choose. This is crucial for making our data analysis more reliable and repeatable. This is the question we're trying to answer. We need to identify approaches that make the SpectralClustering algorithm's results less sensitive to the number of clusters we choose. This is crucial for making our data analysis more reliable and repeatable. This section introduces the core concept: optimizing parameters in scikit-learn's spectral clustering algorithm. The goal is to make the clustering results less sensitive to changes in the number of clusters, a parameter often denoted as n_clusters. Think of it like finding the sweet spot for this parameter to achieve robust clustering across different data scenarios. The problem is that the clustering results are too sensitive to changes in n_clusters. If you change the number of clusters slightly, the entire grouping of data points shifts drastically. This indicates that the algorithm is struggling to find stable and consistent clusters. We're trying to fix this fragility. We explore strategies to improve clustering stability. The question asks which techniques reduce the dependence on the choice of n_clusters. It's all about making clustering more reliable. We're looking for approaches to strengthen the algorithm's performance. Increasing n_neighbors considers broader relationships between data points when creating the affinity matrix. It's like expanding the search radius to identify similar data points. This generally leads to more robust cluster assignments, less affected by minor adjustments to n_clusters. It's about taking a wider view. Decreasing gamma in the radial basis function, RBF, kernel widens the Gaussian kernel used to create the affinity matrix. This leads to a smoother representation of data relationships and a more stable clustering, less dependent on small data variations or n_clusters choices. Think of it as smoothing out the data representation. Using an alternative affinity matrix, like nearest_neighbors, changes the way data relationships are captured. This can affect the resulting cluster structure significantly, potentially making the results more stable with respect to n_clusters. This offers a completely different perspective. For clustering, scaling data using standard scalar is a crucial step in many machine learning tasks. It ensures features with large scales don't overwhelm calculations. Although beneficial for overall clustering quality, it doesn't directly address the issue of n_clusters sensitivity. It's a good hygiene practice, but not the primary solution here. This title simply introduces the topic. We are looking at ways to make spectral clustering more reliable, specifically focusing on how to make it less sensitive to the number of clusters we choose. Increasing the n_neighbors parameter means considering more data points when building the connections between data. Think of it like expanding your social circle. You'll get a better understanding of the overall group dynamics, making the clustering more stable and less prone to being influenced by a few odd points. The gamma parameter controls how wide the influence of each data point is. Decreasing it makes the clustering less picky about small differences between the data points. Instead of tightly clustered groups, the algorithm will smooth things out and consider wider groupings, leading to more consistent results regardless of how many clusters are selected. The affinity matrix defines how the algorithm measures similarity between data points. Using a different matrix type will change this similarity measure. This could significantly affect which points the algorithm groups together. Think of it like choosing different lenses to view your data. It can reveal different structures and make the clustering more resilient to changes in the number of clusters. Standard scalar helps to prevent any one feature from dominating the clustering process by adjusting all features to have a similar range of values. While generally a good idea for improving the overall quality of your clustering, it won't directly solve the problem of sensitivity to the number of clusters.